In this video, we will talk about what the net change theorem is. So the net change theorem is just the fundamental theorem of calculus part 2 stated another way. So it says that if we have the integral from a to b of a derivative function, so I'll call this f prime of t, well, the fundamental theorem of calculus part 2, so by FTC part 2, what it says is that we'll take the antiderivative of this function, which would be f of t, and then you plug in the b and the a and you subtract. So we'd get f, the original function, evaluated at b, minus f evaluated at a. So conceptually what the left-hand side is it's an integral of a rate, it's the integral of the rate of change of f from t equals a to t equals b. So if you take an integral of a rate of change, that's equal to, and the right-hand side is telling me, well, whatever that quantity f is, how much do you have at b, and then how much do you have at a, at those, let's say, times. And then when you subtract those, that tells you how much is that quantity changing. So this is the net change in the quantity f from t equals a to t equals b. Okay, so let's look at an example. So e.g., for example, if we let p prime of t be the projected rate of change of a company's profits. So capital P of t is the profit function. In this case, projected profits. Maybe we're talking about profits in the future. So P prime of t would be the rate of change of the profit. That's why it's saying it's the projected rate of change of a company's profits. And t is in years from 2021. So in the context of this, then if I formed the integral from 3 to 5 of P prime of t, well, using FTC part 2, we do the antiderivative, which is capital P, at evaluated at 5, and then subtract evaluating it at 3. And if I think about what this means, well, this is the profit 5 years from now minus the projected profit 3 years from now. So when I subtract, this is the change in the projected profits. The projected profits over this time interval from t equals 3. Let me just say what that is in terms of years. So if t is 3, that would be talking about the year 2024. 2024, that would be t equals 3 years from now, from 2021, sorry, to when t is 5, that's the year 2026. 2026, that is t equals 5. So that's what this integral would mean. That's how we interpret it. All right, let's do an example where we actually do some computations. So in this example, it says to let v of t be t to the third minus 3t squared plus 2t feet per second. Let this be the velocity of a particle moving along a line at time t seconds, where t is greater than or equal to 0. During the time period where t is between 0 and 4, find the, part A says, displacement. Okay, so recall that displacement is a change in position. Change in position, and I'm going to call my position function s of t. All right, and I can find a change in position if I take a definite integral from a to b of velocity, because velocity is the derivative of position. So if I do fundamental theorem of calculus part 2, we would get the antiderivative of s prime, which is s, and we'd evaluate that. Let me write s of t vertical line, let's plug in the b and the a, and that would give me s of b minus s of a. But s of b minus s of a, well, s of b is the position when t is b. S of a is the position when t is a. When I subtract those, this tells me how much does my position change, or it's, in other words, it's the displacement. Okay, so for our example, let me zoom it out a little bit. We are after this displacement. So we have to evaluate an integral. My time period is from 0 to 4 of velocity. Okay, so we have the integral from 0 to 4. Let's write our velocity function. T to the third minus 3t squared plus 2t dt. Now we got to evaluate this antiderivative. Okay, so antiderivative of t to the third using reverse power rule. We'd get t to the fourth divided by 4. For 3t squared, we'd get minus t cubed. And for plus 2t, we'd get plus t squared. Okay, so now I'm going to put a bracket around all this. I'll write my vertical line to indicate I have to plug in 4 and 0 and then subtract. So if we plug in 4 into this, we'll get 4 to the fourth over 4 minus 4 cubed plus 4 squared. Whoops, sorry, this should be plus 4 squared. And then I got to subtract what I get when I plug 0 in. So I'm going to put a big old parentheses. And if I plug 0 into this, well, I just get 0 minus 0 plus 0. Okay, so that whole thing will just be 0. But in the front, 4 to the fourth divided by 4 is just 4 to the third. So that'll cancel with this 4 to the third, and I end up with just 16, because that's what 4 squared is. But what are units? So units of position, because displacement is change in position, and this problem would be feet. Okay, so that is my displacement. It's 16 feet. All right, so part B of this question asks us for the distance traveled, the total distance traveled by that particle on the interval from 0 to 4. So I want to begin by reviewing what the difference is between displacement and the distance traveled in general. So the discussion I'm going to do in this sort of pink circled region, this is not specific to this question. It's a general thing, so not specific to this problem. It's more of a general thing. Okay, so I have this number line here, and I've drawn tick marks at some of the values. Okay, so now imagine I have this particle that starts at 3, positive 3. Okay, so I'm going to draw that up here. And it starts to move to the left. So it starts to move to the left until it gets to the point where negative 3 is. So it's been moving this way. I'm going to draw some arrows. And then once it reaches there, it's going to change directions and go back towards the right. Okay, so to indicate that, I'm going to just draw the curve a little bit lower. But imagine it were just to go in a straight line. And it does this until it reaches this x value of 1. Okay, so it changes direction. It goes this way. So I'm saying that this particle starts here. And it ends here. So if we think about the displacement, displacement is just the change in position. It's the ending position minus the starting position. And the ending position is 1 on the x-axis. The starting position is 3. I got to subtract those, and that gives me negative 2. So if I think about it, where did my position start? It started at 3. Where did it end? It ended at 1. So what was the change? Well, it changed by negative 2. The position sort of decreased by 2 units. So displacement can be a negative quantity. Okay, but by contrast, for distance traveled considers each of these movements as positive. So this is going to consider all movement as positive. So we have to measure that movement to the left and the movement to the right as positive distances. So when we went from 3 to when x is negative 3, that was 6 units. I got to consider that as positive. And then plus when I went from negative 3 to positive 1, that's a distance of 4. And if we add those together, we get 10. And that is the total distance traveled. With displacement, it measures movements that go in the negative direction as negative. So when we went from 3 to negative 3, it counted that as negative 6. Then when we went to the right, it counted that as positive 4. So negative 6 added to 4, that gives us that negative 2. Okay, so how do we set up an equation for the distance? I'm going to do this with an integral from a to b, so a general integral. But I want some way to consider all of the movement as positive, whether we're moving to the right or we're moving to the left. So the way I'll do that is we'll take the absolute value of the velocity function. Okay, because that'll make all movements positive. Okay, so I'm going to highlight this. This is our formula in general for distance. Okay, so in our example, we are ready to tackle this. So our distance in our problem, we wanted to do it over the time interval from 0 to 4 of the absolute value of our velocity function, which was t to the third minus 3t squared plus 2t, absolute value dt. So this in here, this was our velocity function. Okay, so I don't know how to take an antiderivative of the absolute value of something. So we need some way to get rid of these absolute values. So recall that if I have the absolute value of some quantity, I can write this as a piecewise function. So it'll equal just the stuff inside if the stuff inside, the v of t, is greater than or equal to 0. But if the stuff inside v of t is less than 0, then when I get rid of the absolute values, I have to put another negative in front of it to make that whole thing be non-negative. All right, so what I need to do is figure out when is this thing, when is my velocity positive and when is it negative. So we're going to try to figure out when our velocity, which is t cubed minus 3t squared plus 2t, when is this whole thing greater than or equal to 0? Okay, but we know how to handle inequalities. We've done this in our class. So we would factor this. We get t factored out, and then t squared minus 3t plus 2 greater than or equal to 0. And then if I keep factoring, I get t times t minus 1 times t minus 2 is greater than or equal to 0. Okay, because the way we handled inequalities like this was to do sign analysis. Sign analysis with the number line. Okay, sign analysis. So we got to figure out, well, when is this whole thing equal to 0 and when is it undefined? Well, this equals 0 when t equals from this t, it's when it's 0. From the t minus 1, we get t equals 1. And from the t minus 2, we get t is 2. Okay, and this whole thing would never be undefined. All right, so we got to take those values and put them on a number line now. So I'll draw a number line. In this problem, it said that t is greater than or equal to 0. So that limits my domain. Okay, so I'm going to put a bracket at 0, and I'm just going to focus on the stuff to the right of it. But I have to put tick marks at 0, which we already have, 1 and 2. 1 and 2. Okay, so let's put all of the factors as rows. So t minus 1, t minus 2. And once we have those, we can multiply them to get the velocity. Okay, so I'll separate out rows. And I'll separate out columns. Okay, so with t, in each of these intervals, it's going to be positive. Remember, I don't worry about things less than 0 because t had to be greater than or equal to 0. So I'm not going to be plugging in any negative numbers over here. With t minus 1, that's going to be positive to the right of 1 and negative to the left of it. T minus 2 is going to be positive to the right of 2 and negative to the left of it. So when I multiply these, whoops, sorry, let's put the negatives in red. Negatives in red. When I multiply these, the middle region is going to be negative. The outer ones are going to be positive. So now we know the intervals where velocity is positive and where it's negative. So when we go to evaluate our integral of this absolute value, we can say thus, our integral from 0 to 4 of the absolute value v of t dt, this is just going to be equal to, I'm going to split it up into these pieces. We'll have an integral from 0 to 1. And on that integral, velocity is positive, so I can just drop these absolute values. I'll just get v of t. And then plus another integral from 1 to 2, but on that integral, velocity is negative. And based on what we said here with the absolute value function, when the inside is negative, when I drop the absolute values, I got to put another negative in front of that velocity function to make it non-negative. So I would have to write negative v of t here. In fact, let me put that negative sign in red. Negative v of t. And this is coming from the fact that coming from the fact that absolute value of v of t is equal to negative v of t when our velocity is negative, and it's negative on the interval from 1 to 2 from my sign chart. Okay, and then we have plus the interval from 2 to 4, and their velocity is positive, so I can just drop the absolute value to get v of t. All right, so each of these integrals is going to be really similar, so I'm going to do the computation for one of them and then just tell you what we get for the others. All right, so for this first one, we have an integral from 0 to 1 of t cubed minus 3t squared plus 2t dt. And evaluating this antiderivative we've already done, is t to the 4th over 4 minus t to the 3rd plus t squared. And then I got to plug in the 1 and 0. Plugging in 1, we'll get 1/4. Let me write that fully. 1 to the 4th divided by 4 minus 1 cubed plus 1 squared. And then minus, when I plug 0 into it, we just get minus 0. Each of these terms will just be 0. All right, so minus 1 cubed plus 1 squared, they cancel. And we just get 1/4. So this first integral is just 1/4. The second one, so if we evaluate this one, I'll just get it started. We'll have the integral from 1 to 2. I have to put a negative in front of my whole velocity function. So if I distribute that negative to each of these terms, we'll get negative t to the 3rd plus 3t squared minus 2t. And if we evaluate this, I'll just put a dot, dot, dot. I'm going to leave those details for you. We end up with 1/4 as well. Okay, so that's just a coincidence. These won't always be the same. Okay, and let's talk about the last one. The last one, I'm just going to tell you what this one ends up being. If we work it out, it ends up being 16. So adding those values, we'll get the distance. The first integral was 1/4. The second one was also 1/4. And the last one was 16. So 1/4 plus 1/4, that's a half. And if I get a common denominator, 16 becomes 32 over 2. And adding these, we get 33 over 2. And the units of distance in this problem were feet. And if I wanted to write this as a decimal, this would be 16.5. So the total distance traveled was 16.5 feet. So if we compare that to the displacement we got in part A, that was 16 feet. So the distance you get can never be less than the displacement. And this problem ended up being greater. Sometimes they may be equal, but the distance traveled can never be less than the displacement. And I want to end by just asking why. I want to leave that for you to think about. It's not too challenging, but I want you to think about why and make sure you know. So in terms of our goals, we just had the one goal for this section, and we've done that. We know how to compute a net change in some quantity using definite integrals.